Robert Habermeier. He is co-founder of Polkadot, CTO at Parity Technologies, Parachains core team lead. He has a background in Rust, distributed systems, and computer security. He's also, according to his LinkedIn, not an automaton. Rob also joined us last year for CSCON 0, so it is an honor to have him come on again to give us a presentation, especially during this extremely exciting time for Polkadot. And if this becomes a yearly tradition, Rob, I certainly would not be complaining, and neither would the rest of ChainSafe and the world, actually. So it is my honor to introduce Robert up onto the stage, who will be talking about Polkadot's launch from a technical perspective. So Robert, if you would like to come on stage. What's up, what's up?
Hey, Tim, wow, what an introduction. I feel like I should, work on my dance moves or something.
Yeah, let's do it. All right, I'll let you take the stage here, and yeah.
Awesome. Yeah, great to be here. Yeah, I've been here last year as well, and I really enjoyed it. I'm back again, after another year of development. Let me pull up the presentation, and I'm assuming that's all good.
Yes.
So yeah, I wanted to talk about the Parachains launch today, which is it's kind of a big moment for Polkadot in general. I mean, we've been working very, very hard on building this technology, and when it comes to Polkadot, there's a lot of things to talk about. I mean, you can look at it from a lot of different perspectives of from the tech, and this is more of a technical audience, so I was going to dive into that a bit more. There's the community, there's the developer tooling, there's the ecosystem. I'm not going to touch on a lot of those things. I'd say that they're all happening. There's cool stuff happening in all of those domains. But I want to give a little bit of a recap, because I don't know how familiar all of you are with Polkadot, or sort of where we've been in our launch. I mean, there's a lot of noise on the internet, and sometimes, if you're not following these projects day to day, you might not have a clear picture of exactly where we stand. So my goal today is really just give you a sense of where we're at with this technology, and where it's going to go over the next couple of years, where our priorities are as a development team, building this base layer. So without further ado, I'll jump into the timeline a bit. What's happened over the past I guess couple of years now at this point. So obviously we had a lot of development work in the run up to the beginning of this timeline. That's the initial commits that were made to our Polkadot repos were at the end of 2017. So we had a 2-year development cycle before even getting to launching value-bearing networks, to the point where we felt confident that this code could be used for that. That involved building out sort of prototypes, doing all of the research, building the substrate blockchain framework, testing it, implementing those bits of research, and so on. But by the end of 2019, we had gotten into a point where we were able to launch the Kusama mainnet. What Kusama is, it's still around today. It's still being used quite heavily, actually, I might add. It's a beta or canary network for Polkadot. So it was one of the first live proof of stake networks in existence, especially from this sort of newer category, like second gen proof of stake, which involves taking classical consensus protocols and slashing and using that to provide consensus as well as economic security. So it was really one of the first, if not the first, to launch with that type of technology. It's the same stuff that's being used on Polkadot today. It's the same consensus protocol, the same slashing mechanism. There have been a few tweaks and optimizations and stuff, but it's really the same code. That's the babe and grandpa consensus stuff. And that, that had a few hiccups, but we had gotten them all ironed out by May 2020. And that was a permission launch by the Web3 Foundation, same technology. And then over that summer, migrating to fully permissionless, transferable proof of stake network. And at this point, we had roughly completed the research that was necessary to build the Parachains technology, which is Polkadot's sharding technology. This summer, Parachains went live on Kusama. So there was first a shell parachain, which is basically it's just a dummy. It's like an identity smart contract or something like that. Roughly the equivalent of that. It would be, it's a chain that doesn't do anything. It grows, it advances, but there's no transactions, there's no value. That's what we use to make sure that the agreement on agreement stuff was actually working in the wild. That was working on the Kusama chain, which is a network with 900 globally distributed validators at a time. I think at the moment it's 1,000. And then there were 5 auctions for other parachains, and at the moment I think there are 15 or 16 parachains live on Kusama. Like they're still going up. And now parachains are imminently going live on Polkadot. In fact, there's already a shell parachain on Polkadot, which shows that the base consensus primitives are working on there. And shortly, the first 5 auctions will begin for parachain slots. Well, actually, the first 5 auctions will conclude, and those parachains that win them will go live. It's hard to pin down the exact date that that's going to happen. It's probably going to be the 17th or the 18th, but it's based on block number. So the governance of Polkadot kind of determined a block number at which those parachains are going to go live, and it's either going to be the 17th or the 18th, most likely, unless blocks really slow down. But one of the things I really want to get across in this talk is the fact that this is really just the beginning. I mean, you could think of it as akin to when Ethereum Frontier first launched, right, in late 2015. The protocol has changed a lot since then. And the code has become much more mature. There have been a lot of optimizations. The client landscape has varied wildly. And I expect kind of the same thing to happen in the Polkadot ecosystem, which is what we're talking about launching here is really just an MVP. And obviously, as these projects grow, you get a lot more surface area to think about really interesting things. And a lot of the speakers at this conference have been talking about Ethereum protocol, or things that are happening in the Ethereum space, and it's amazing to see like how this surface area really blows up and expands. And this is really an end. This is really a beginning and not an end. I want to take a quick detour through the scaling technology landscape just to give a bit of background on what are the options and what are people talking about lately. So I think you have three main buckets, and these first 2 are rollups, optimistic rollups and ZK rollups, and this is what you would typically refer to as L2 scaling, especially within Ethereum space. These are the primary forms of L2 scaling that are being discussed. And then you have sharding as well, and sharding being consensus level. So I want to go through some of the differences, the advantages, and the drawbacks of each of these, and then sort of connect that to what we're doing with Polkadot with Parachain. So with an optimistic rollup, what you're talking about is an L2 blockchain. So it's a layer 2 blockchain. It's a second blockchain where the headers, or something like a block header, that contains a commitment to the full state of all accounts and contracts and things, get posted to the L1 chain. And what you do is you basically you allow certain groups or individuals or actors to post those headers, and then you wait. You have a waiting period where anybody's allowed to challenge them and like prove that they're bad. And if they do turn out to be bad, then there's some slashing mechanism on the L1 chain, or there are a few different ways to do it. But that's the rough concept. And I think the advantages to this is you have very, very fast execution. As long as everybody's behaving well, that's why they're called optimistic rollups, because as long as everybody's behaving well, it proceeds very quickly. But you do have this slow finality because you wait for these long fraud periods, and if there are actors who aren't behaving well, it can really, throw a wrench into the gears of the system. So, those are the benefits and the drawbacks. I think people can already build optimistic rollups today. They're not particularly difficult. I mean, you won't do one in a weekend, but you'll certainly be able to do one with a few developers over a few months or a year. Very interesting is the second category, which is the zero knowledge rollups. I mean, this is really incredible field of math that's been developed for decades of zero knowledge proofs. And what this is mostly about is sort of proof combination and aggregation. Like everybody kind of gets to prove that their transaction was valid, and then you have these aggregators that are rolling up, hundreds or thousands of these proofs into a single proof. And then the layer one blockchain can validate all of those transactions at once. Now, that's really cool. It's an incredible property of zero knowledge proofs that you can verify stuff faster than it takes to execute. I think that's a sort of a probabilistic escape hatch, but it's overwhelmingly unlikely that you would verify something bad to be true. But it's very expensive to prove and aggregate these things. It might be very high CPU. In the end, it might encourage centralization, and the state-of-the-art technology, on paper and in implementation, is quite far away from fully general execution. We are now, really interestingly, seeing the first forays into that type of thing, but it has not really, been developed to the point of actual usability. And I think the general consensus is that it's at least a few years away. So then there's also sharding, which I'm sure you've heard a lot about, which is about consensus level changes to split work across a validator set. The core takeaway being that not everybody executes everything, and then it's very hard to guarantee security. It scales, but only quadratically, at least if you have message passing. It's very technically difficult to implement because you can have cascading failures if one shard has a bad transaction, and that pollutes another shard, which pollutes another shard, and then all of a sudden your whole system is kaput. But you can have very fast finality and fast agreement and incredibly high throughput in a sharded system. A lot of it comes down to just clever engineering once you get the protocol nailed down, just to improve the networking code and reduce those bottlenecks. Even though it scales quadratically, I expect that sharded systems can be pushed very high in throughput. So we use a form of what we call heterogeneous shard in our parachains technology. So every parachain defines its own validity criteria. It defines what a block is composed of, what data it needs to check that a block is good, and what executes in order to check that a block is good. Maybe one day this could all just be zero knowledge proof stuff, right? Where the proof data is just some kind of cryptographic witness, and the validity function is just some circuit checking logic. But for now, this is WebAssembly, right? This is subsets of Merkle trees or other cryptographic accumulators, and as the input data, and the witness function is or the validity function is just a WebAssembly blob. So it's heterogeneous sharding in that every blockchain kind of does its own thing. Now, I could have an entire talk about like all of the different things that people are doing with this primitive of writing their own blockchains. But for now, I want to keep this at a higher level of abstraction. We just kind of know that all parachains are doing a separate thing, but that's not really the main focus point of how do we scale the protocol and how do we make the protocol faster. And I have a couple diagrams here as well, just to sort of nail that down. The way that Polkadot works effectively is that it's providing, we have one chain we call the relay chain. This is sort of akin to the beacon chain in Ethereum, in Ethereum 2.0, which is sort of providing scheduling and and consensus and security for all of the registered parachains, so they advance in lockstep. And the way I like to frame this is that, if you want to 51% attack one chain, you have to 51% attack all the chains at the same time, because their fork choice rules move in sync with each other. And that's sort of the mechanism that we kind of get an advantage that optimistic rollups don't have. In an optimistic rollup, you don't have influence on the layer one's fork choice rule or finality rules. In sharded systems like Polkadot parachains, a bad parachain can actually be avoided on the layer one fork choice rule. So that's, I think, a key differentiation. You can also have some parachains that are bridges. They could bridge to Bitcoin, they could bridge to Ethereum, or you could, go one level further where there's an EVM parachain that implements a bridge, and that bridge connects to all the other EVM parachains or things like that. So it's heterogeneous sharding. This diagram kind of shows that a bit. We have a few different key actors. We have collators who actually author. They know how to create valid blocks. Validators get moved around all the time. The only thing they need to know how to do is validate blocks and move data over the internet. I want to move on and talk a bit about basically optimizations, because everything that I've talked about so far, this is implemented already. This is what's launching on the 17th or the 18th. The next step for us is really, on the protocol side, it's all about engineering and optimizations. The framework and scaffold that we have gives us a lot of room to maneuver. We've done essentially the most basic version of parachains. It works, but the upgrades that are going to be coming over the next year, the next 2 years, are just going to make it a lot faster. And that's upgrades within that Parachains V1 model, and also within that Parachains V2 model, which is, the further out pie in the sky style research of what happens if we're running multiple relay chains and moving validators between those relay chains. That's the really far out stuff. That's the stuff that's really going to ratchet up the scaling even further. But even within this Parachains V1 model, if we have one relay chain with a bunch of parachains attached, and those parachains are the leaves of the tree. They don't have their own parachains or anything like that. Even within that model, there's a lot of room for optimization. And this is the near term stuff. So you guys are generally, I guess, a developer audience, and you can appreciate the near term optimization and engineering effort that's going to go into this. So the main things that are coming up from the system, and the rest of this talk, actually, I'm going to dedicate to I think what is the biggest one of these is asynchronous backing, which is it's a protocol level change that allows parachain blocks to be pipelined and prepared well in advance of inclusion on chain. What this essentially means is that, well, right now, if you look at like Polkadot or Kusama, parachain blocks are coming in once every 12 seconds. They can come in once every 6 seconds, and beyond that, they can have we can spend much more time validating parachain blocks than we do currently. At the moment, we have a soft limit of half a second of execution time given to each parachain block by validators. And the goal is to get this up to something like 3 seconds per 6 seconds instead of 0.5 seconds per 12 seconds. Furthermore, the goal is to get more witness data. More data is more throughput. We're also interested in parathreads, so dynamically scheduling parachains. This is an optimization in the sense of it allows the system to have more parachains by attaching them as parathreads. These would be sort of a middle ground between the deploy a smart contract and build your own 24/7 blockchain, pay as you go parachains. This is I think a really important factor. And then a bunch of networking optimizations. Like our networking code is, it's functional, it's fine, but there's a lot of really clever stuff that you can do. Taking more inspiration from things like BitTorrent, playing around with the topology, scale-free networks. There's a bunch of ideas that we have floating around on the research side that will enable us to transmit data over the network more quickly, which is probably, if asynchronous backing works, networking will become the primary bottleneck. So with that in mind, I want to dive into this asynchronous backing thing because it's the main roadmap item coming up. So the goal is to release a version of the node that does this type of thing sometime in the next few months. So I want to dive into the two parts of this term. So backing is the process by which validators accept and attest to the validity of new parachain blocks. Essentially the mechanism by which we get skin in the game. It's not a security mechanism, except that it gets skin in the game. There are other security mechanisms, but one of the nice things about our design is that the inclusion process of making sure that stuff gets referenced on chain is different than the processes that actually provide security and finality, which means that we're in this really nice space from an engineering perspective where we can optimize without worrying about breaking safety. We might break liveness, if there's a bug that causes a stall, but at least you won't break safety. So that's kind of a nice place to be optimizing from a practical standpoint. Backing is about notifying the relay chain that of the header of a new parachain block, and that enough validators from its group or committee have actually signed off on the block. By asynchronous in this sense, I mean that we disconnect the progress of the backing system, of the backing process, that's supposed to say, sorry, from the growth of the relay chain. So right now, they move more heavily coordinated. They're more synchronized with each other. You can't start building the next parachain block until the next relay chain block has appeared. And this is mostly for architectural reasons about you have to know the state of the message queues before you come in and build a new block, because you have to know what the latest states of the message queues are and things like that, or what the most recent block header that's referenced on the relay chain is. So that's why those things are more synchronized now. And we're looking at a set of optimizations that will allow them to become asynchronous. So the next few slides, I want to walk through basically what this really gets us. So on Polkadot, blocks are 6 seconds. So we have relay chain block 1 to relay chain block 2. The arrow on the relay chain indicates a parent relationship, right? So R1 is the parent of R2. On the lower level of the diagram, it's about the flow, sort of the actions that are being taken. So validators see R1 being built, and they'll start doing this backing process. It basically means they'll get a parachain block from a collator, they'll check it, they'll start signing off on it. Once they have a quorum, then they can submit that quorum to the relay chain, right? And this is fine if you can do it in 6 seconds, right? If you can do it in 6 seconds, if you can get it from a collator, get enough people in the committee to sign off on it, and then get it to the block author who actually includes that in the R2 that they author, that's fine. But what happens fairly commonly is that you're just a little bit too late. It doesn't come in 6 seconds, it'll come in 8 seconds, or we'll get the consensus done in 6.5 seconds. It doesn't matter. As long as you're too slow, even by a little bit, that's not getting included. And that's kind of a problem, because when things are working smoothly, you have this repeated cadence of backing, inclusion, backing, inclusion. You get this this rhythmic thing. But if things are off even just a little bit, consistently, the parachain might stall until the network can make a block fast enough to break that stall. Even though things are just being missed by a little bit, we constantly have to go and start from scratch. And if you go on, the explorers for Kusama, you see this happens sometimes. And this is what it can be pretty much entirely attributed to. But the interesting thing is that this is totally just it's just a factor of us not using the scaffolding of the Parachains protocol to our full advantage in our implementation. Right. So what we're launching right now is something like the minimal version, but essentially over the next 2 months we're going to get it to look something more like this, which is if by some accident you accidentally take 7 seconds instead of 6 seconds, that's fine. You can just reuse that result in the next relay chain block, and you can also immediately start building the next parachain block on top of that. And the goal here is to totally decouple the extension of the parachain from the extension of the relay chain, so that whenever you author a relay chain block, there's always at least one new parachain block ready to be included on the relay chain. So that's the goal of this optimization. And the reason I want to talk about it is because that's sort of the thing that me and my team are working on now as our main protocol optimization. So always helps to talk about what's currently going on. And yeah, so this is the thing. There is a there's a big GitHub issue right up on that. That's going to get transformed into something of a loose implementable spec. We have a document which is called the Implementer's Guide, which has been the primary implementation document of the Polkadot node. And the idea here is to specify the behaviors and interfaces of all the components that go into a node, both on what we call the runtime or blockchain logic half of it, or also in the node side, like networking and execution layers. So that's going to be transformed into an amendment to the implementer's guide, and then from that we would actually know exactly which changes we need to make to the code base. So keep an eye out for those changes. We should have this on the test nets sometime early next year. Oh, and I wanted to go into this in a bit more detail. So just reiterating what this diagram means is that even though we missed the window of opportunity, we can still include the parachain block in the next relay chain block instead of starting over. And we've already started backing the next parachain block even before then. So that those labels might make it a little bit easier to understand. Summarizing exactly what the goals are here is more time spent executing transactions, because it doesn't matter if we miss our window slightly, and we'll also be building these things optimistically off chain. And anyway, so there's always going to be something ready to include. Less risk of wasted effort. The downside of wasted effort, or the downside of missing the window is much lower, and larger proofs of validity. All of these things together mean smoother block times. They mean more execution, and they mean more data going into that execution, which translates to more throughput, all in all. More predictability, more throughput, lower latency, all of that stuff. And we have less reliance on speedy internet, because right now, with that short window, it's encouraging validators to move closer to each other geographically so that they can try to make that very narrow window. Latency is a non-negligible factor. After these changes, latency won't be nearly as important, because it'll be, we'll be dealing with longer block authoring windows, where execution and bandwidth are going to be much more important than latency. More time to author and execute blocks combined with that means more decentralization. So we will have, validators that are more distributed globally, that feel comfortable being more distributed, so that we won't have this implicit reward points system pushing them closer together. It won't be as much of a factor, and we'll be able to accept, say, less stringent hardware requirements on validators. So I'm going to leave you with a couple of takeaways. So one, Polkadot Parachains are just launching, and this is only the beginning of our engineering efforts. In the meantime, we're building up our engineering teams a lot to focus on these things as well as others. So we are hiring for that, and we have a lot of sort of low-hanging fruit for optimization, our protocol and our code. Anybody who's worked on a blockchain node knows how complex these code bases can get, and how often easy and gratifying it can be to just trawl through them and find issues or optimize some subsystem. So thanks for attending, everybody. I don't know what time it is, but if I have time for questions, I'd love to answer some of them. So thank you for that.
Awesome. That was an amazing talk, Rob. Thank you so much. We do have a bunch of questions, so we'd be happy to hear your insights on some of them. First one from Jimmy with 5 upvotes. Way to go, Jimmy. I know Polkadot has a shared security model, but how important is individual parachain security? Does the Polkadot network prevent or mitigate against a malicious or corrupt collator set?
Yeah, that's a really good question. So I think the easiest way to break this down is that parachain collators are only responsible for liveness. So they're basically only responsible for is somebody creating new parachain blocks. If you don't have any collators, nobody's going to be making blocks. If there's one collator, then only that one collator is going to be making blocks, and they'll kind of have control over what gets included in those blocks. So it's good to maintain a healthy collator set. The relay chain validators are completely responsible for the safety of the parachains. So that is, making sure that, and the way that we frame this is, no parachain block should ever appear in the finalized part of the relay chain unless that parachain block has passed the validity function. So we heavily integrate parachain validity with relay chain finality. So it's an integrated part of our fork choice rule. We have 2 security protocols, which are called approvals and disputes. What approvals is about is using a technology called VRFs, which is sort of like verifiable dice rolling. Like I can roll, and I'm talking about like a gajillion sided die and prove to you that this is what I rolled, to have validators self-select to check the parachain blocks randomly. And we make a security argument with Gambler's Ruin, which is that we have enough people checking that at least one of them needs to be honest. And if any of them are honest, then it will be escalated. And if there's an escalation, everybody checks it, and whoever's wrong will get slashed. There are more complications and sort of edge cases to the approvals protocol, which is like what happens if people say they're going to start checking stuff and then they disappear. That means there's probably an attack, and then we have like a replacement protocol as part of that. We do have write-ups on all of this stuff. But to answer your question, parachain validity and safety is incredibly important.
Okay, we'll get 2 more questions in there just because we're running a little bit behind on time. So I'll just go for the next 2 with the highest upvotes. So one from Anonymous with 4 upvotes. Will we see a dedicated parachain for bridging or more spread around bridges on different parachains in the future?
I expect that we're going to see like a lot of different approaches to bridges. So we'll see, people who are doing more custodial style bridges that are just launching smart contracts on some smart contract enabled chain on Polkadot, like Moonriver or Moonbeam or Plasm or Astar or whatever, is doing smart contracts on Polkadot. They'll probably launch things like that. We would like to do a parachain that is a substrate to substrate bridge hub chain. So, bridging and verification of bridging might not be that expensive. So you might be able to combine lots of these, especially if they're all using the same consensus protocol, onto one hub chain where the messages pass through.
For that. And then one more from Light Client. Thanks for sticking around, Light Client. Do parachain block producers rotate between parachains? If not, how do you feel about their ability to be corrupted, whether censorship or data withholding?
Yeah, they don't rotate between parachains. Collator selection, so parachain block producers, is it's a process that's entirely up to the parachain. So there's nothing on the Polkadot side that actually dictates that you even need to have a bounded collator set, although a lot of the optimizations that we'd like to do rely on having parachain block producers that are probably unique for that time slot. But a lot of parachains are using staking palettes, or even have tens or hundreds of collators that rotate or are chosen randomly with VRFs that are unpredictable. And we've designed our consensus protocol so they also work for parachains as well. So we think that that's about as good as any other proof of stake network.
For that. And also, we're going to mark down all these questions, and we can maybe like shoot them over to you so you can answer on Twitter if you want. But otherwise, thank you so much for your time. Really, really appreciate you taking the time out to drop by and give us a talk and presentation. And hopefully we can do it again next year, or maybe even sooner.
Yeah, for sure. It was great to be here, and hit me up next year.
Yeah, awesome. And feel free to stick around. We got Joe Lubin and Aiden coming up. Thank you so much for your time. Really, really appreciate it.
For sure. All right. See you around. Bye-bye.